So today we're going to learn about dot products. So basically, what are dot products? Now, dot products are one method of multiplying a vector to a vector. So I have two vectors, vector A and vector B. To perform the dot product, we first write the notation, right? So the notation is simply the dots we use for multiplication and different variables before. So don't use the cross here because that's a different way of multiplying. But okay, so right now the dot product we have vector A times vector B is equal to, so is our answer a vector or a scalar? Now here our answer is actually a scalar. So how does this work? So that C is actually a scalar, not vector. So let's say I have x1, y1 dot x2, y2 the answer here is going to actually be equal to x1, x2 plus y1, y2. So we multiply the corresponding components indeed, but we add them together. And this is a scalar because x1, x2, y1, y2 are all scalars. They're coordinates, right? So they're all scalars. Scalar times scalar is scalar. Two scalars summed together is also a scalar. So the answer C is a scalar. So now let's just look at a few examples of using the dot product before we go into more in-depth formulas. So firstly, let's say I have the example 5, negative 2. I want to dot this by, let's see, negative 3 and 4. So what I can do here is now I have 5 times negative 3, or x1 times x2, plus negative 2 times 4, y1 times y2. So that's actually just equal to negative 15 minus 8, which is negative 23. So that's our answer. So we try another example. We have, so let's say now I want to try three-dimensional vectors. So for three-dimensional vectors, let's just say I have 3, negative 2, and 4 times 5, negative 3, and negative 1. Okay, so our answer is going to be equal to, so we still multiply the x components. We have 3 times 5, and then we also have the y components, negative 2 times negative 3. We also have the z components, 4 times negative 1. So essentially you still take every component that corresponds, you multiply them together, you add them to other components corresponding, multiply together. Okay, so now let's just evaluate this. So we have 15 plus 6 minus 4. This is going to be equal to 15 plus 2, which is 17. Okay, so now we've finished some basic of the dot product. We came with 2 examples. You can come up with more examples and work through them if you wish to practice. But now let's just talk about this important formula we have. So let's say I didn't know the components of my dot product, of my vectors, which is kind of common in problems, right? Like we don't know the components in vectors. So how do we figure out the dot product now? So I still want to figure out the dot product of vector A and vector B. How do I achieve that? So now this is going to be equal to the magnitude of A times the magnitude of B. Times cosine theta. Now as you can see, theta is obviously an angle, and this is equal to scalar c. Now why is that? And what is cosine theta? So what's theta first? So if I just drew the two vectors, that's vector A, that's vector B. The angle between them is theta. Okay, so why does this formula logically make sense? Or how can we logically remember it or make sense of it? Because right now we're kind of confused why this works. So basically you can imagine, my vectors can be imagined as two forces, right? Like, I mean, you can imagine that these are two people, there are two people, A and B, and they're pulling something. So let's say they're trying to drag this heavy, they're trying to like pull this heavy carriage. So this is our carriage and we're starting to pull this. Now however, so the magnitude of A is kind of like the force used, right? Like A is, so that's the number of force used. B is also the force that person B used. However, now they're not pulling in the same direction, which is the problem, the major problem in our vectors. They're not pulling in the same direction, so the resulting force won't just be the magnitude of A plus the magnitude of B. It's actually cosine, so you have to actually multiply this by cosine theta, which is like the efficiency of the forces combined, because if we look at the cosine graph, which is something like this, so yes, something like this. This is x, this is y. It starts off at 1, it goes to -1, then it goes back to 1. So if I let this be more accurate, it will be something like this. Yes, so that's 0 to 2 pi. Okay, so now how does this make sense for the cosine graph? Because like the cosine is changing constantly, right, for every different angle theta. So why does this formula here work? So let's just imagine that we were pulling two objects at an acute angle. So sorry, we're pulling this object at an acute angle, like we have in this diagram. So this theta is acute, right? So at this point, when you see that the angles between before pi over 2 and after 0, so acute angles all have a cosine of positive values. Now that is indeed making sense, because although the fact that if we pull this object here in different directions and the effect is not the maximum, there is still some effect because we're pulling it in a, if you draw a big enough arrow, a rough enough trend. So the object is still going to move a bit in some direction, right? Now how much is this a bit compared to the maximum force that could have been used? Now this a bit is the cosine value. So what about the 1 here? So this part is 1. How does this make sense? So in this case we have a cosine angle, we have a theta of 0. So basically, our two objects are like, our two forces are like literally like this. So you can imagine if I multiply them together, I just want the total force used. Now in this case, we're literally pulling in the same direction. So this is the maximum efficiency we can get. Like we're pulling in the same direction, so both of our forces are used to the extent. So we have an efficiency of 1. Because basically we just have the magnitude of two forces applied together, which is like the total efficiency. So now for the acute angle, I've already explained that. It's basically like you're pulling in a tiny bit similar direction, but so it's going to move a bit to where the force is greater. So here the magnitude of B is greater than the magnitude of A, so the object is going to move a bit more in this direction here. So it's actually going to move like somewhat diagonal like this, closer to the green vector. Okay, so what about the 0 here? So the 0 here is going to be vector A. We have vector A here, vector B. We have theta is 90 degrees, or pi over 2 radians. So how does this exactly work? So if we pull two things in like a different direction, like this direction is like literally different. Now I know that it looks like the object is going to move this way a bit because of the force. However, in this case, we can think about it as like, so we can think about this as like we have the object and we're moving it in like different directions, so we're not cooperating. Because even here, we're moving it in roughly the same trend. However, here, we're not cooperating. We're literally moving it at different directions. Our goal is different. Like, we're literally moving it, so this way can be north. We're moving this northwards. We're moving this to the east. Our goals are different. So yes, you might think it's going to move to the northeast direction. However, that's not how it works. We're trying to figure out the efficiency now. The efficiency is just 0. Because no one's cooperating. We're not helping each other. So you can say that the efficiency is 0. So now let's look at what happens with the negative 1 part. Because for the negative 1 part, like how does the negative 1 occur? Like where does negative 1 come out from? So you can imagine this as two vectors in the completely opposite directions. So you're going to think, isn't it this 0 because we're not actually moving? Or we might be moving in a direction where the magnitude is greater? Maybe, but... So maybe, however, right now, we're completely not cooperating. So this person's actually opposing the green vector. Like, person A is actually opposing person B. Person A doesn't want to go in that direction person B is going. They're opposing each other. So now the efficiency, you can imagine, is negative, and precisely negative 1. Even here, we're not cooperating, yes, but we just have different goals. We're not trying to stop each other. We're just trying to achieve our goals within our own strength. Here, we're literally trying to oppose each other from getting to their own goal. So the efficiency is going to be negative 1. So you can imagine this is why the formula works. Now this formula can be usefully rewritten into cosine theta is equal to c over the magnitude of vector A and times the magnitude of vector B. Now this formula can be useful when people want you to figure out the angle of theta. Like they are like, here's a scalar, here's the vector A, the magnitude of vector A and B, now what's the angle? Then you can use this formula, and you can just plug this into the calculator. For cosine theta, you can just plug the inverse into the calculator. So, thanks for watching.